Hello there. Suppose I have a particle and I'm tracking its location in space with some coordinate q. Now, q is a generalized coordinate, which means that q could be a Cartesian coordinate x, a radial distance r, an angle theta, or something else entirely, but we're somehow tracking the position of our particle with some coordinate, and that particle is subject to conservative forces, which means that the particle's total energy E here, which can always be written out as some potential energy term plus a kinetic energy term, will be constant. And so what I've set up on the right here is, let's go ahead and suppose that I'm in the lab and I've set things up such that I have a potential energy function of this arbitrary blue shape here. Okay, my particle is subject to the conservative forces which make this, this arbitrary potential energy shape. And so what I do is I come in very, very carefully and I place my particle at this potential energy minimum location, which we're calling Q0. Okay, if I do that very carefully and I just place the particle there, that means my particle starts out with no kinetic energy, and so this term goes to 0 here, and so the total energy of my particle is just going to be this red line E here, which is tangent to the potential energy minimum. Next, what I do is I give a very slight flick to the particle. What I'm doing is I'm giving my particle a small perturbance. Okay, so I deliver a very small amount of energy, this little delta E here, and that very slightly shifts up the total energy of my particle. And so when we do this, our particle is going to oscillate between these intersection points where this new energy line intersects the potential energy curve. Okay, I talked about this in the last video, right? So let me go ahead and call these Qi and Qj. Just so we're totally on the same page. The particle is going to oscillate back and forth between Qi and Qj. That is a general argument that has nothing to do with the fact that our energy perturbance, this delta E here, it could be a small or a large perturbance. That's merely a fact that we're within this potential energy valley. Now this is the specific argument. Because my perturbance is very small, that means that this width here between Qi and Qj, this is small. This is a small width. Okay, so we have small displacements from our equilibrium position Q0, some small delta Qs. And if we have small displacements from our equilibrium position, that means our particle is going to oscillate in a very specific way. It's going to experience simple harmonic oscillation. Let's see how. Okay, so I have this smooth function here, okay, and that means I can Taylor expand this u of q out, right? So if I Taylor expand about q0, I'm going to have u as a function of q is equal to u evaluated at q0 plus our linear term du dq evaluated at q0 times q minus q0 plus, next is our quadratic term, 1/2 d squared u dq squared evaluated at q0, and this of course is times q minus q0 squared plus our higher terms, which I'm just going to say ... We only need to worry about the first 3. Right, so all that I've done here is I've taken this arbitrary curve u of q. Look, it's a smooth, well-behaved function, and I can write it out as a Taylor expansion about q0. So far we've just used mathematics. Now let's apply the physics. This is a potential energy curve, and we're expanding about a potential energy minimum. Let's go through one term at a time. Now, this first term here, which is just our constant term, right? This is like a constant here. This is just the absolute height of this potential energy minimum, right? It has no physical significance because absolute heights and potential energy are pretty meaningless, right? A really quick way to see that is we know that, to get from potential energy to force, you have to take the minus gradient of your potential energy to get to force. And if you've never seen the gradient before, this just holds derivatives in it, right? And so if you take the derivative of a constant, that's just going to give you 0. So the actual dynamics, right, contained by the force, that doesn't care about the constants in your potential energy function. Those just go to 0 when you take the derivative. So this constant here, we either ignore this or we set to 0. We shift our entire potential energy curve such that the location that we're interested in, we just say has a potential energy of 0. But anyway, so that's a pretty trivial term. The second term in our Taylor series, this guy, well look, if we're evaluating this derivative here, du dq, at this minimum, right? What's the slope doing here? It's just a horizontal line. This derivative is 0, which means the first non-trivial term in this Taylor expansion is this third term here. Okay, and so what we're going to do then is we're going to truncate the Taylor series at just this third term here. So we're going to say that u of q is approximately equal to 1/2 d squared u dq squared evaluated at q naught times q minus q naught squared. So we've truncated off these higher order terms here. How physically relevant is it to just truncate the series after the third term? Well, it depends on what the fourth term looks like, right? If I have some q minus q naught cubed here, right, then depending on the size of this guy here compared to my second order term here, that's going to tell me the physical validity of me saying, all right, let's stop the Taylor series at the third term, right? And the quality of this approximation is going to depend on how small these displacements are, how small these delta q's are from the equilibrium position q naught. All right, so if we're feeling excellent about that, now this is really powerful. Right, and so this guy here, this derivative here, this is just going to give us some number, right? To emphasize that this is just a general number, let me go ahead and call this chi. So I can say that u sub q is approximately equal to 1/2 times chi times q minus q naught squared. Right, and so if we compare this to the potential energy of, say, a spring, right? If I have a 1D spring, then its potential energy is going to look like 1/2 times k times x minus the equilibrium position x naught squared, where k we would call the spring constant, right? So this guy here, this is a Hooke's law spring potential energy, which is typically the first example of simple harmonic oscillation that we run into in physics. Right? But let's go ahead and just really emphasize the fact here that these forms are identical, right? And so likewise, if we track this particle's coordinate q, we're going to find that it also exhibits simple harmonic oscillation, right? So this is a very general kind of condition. As long as we have small enough perturbances from our equilibrium position q naught, we're going to find that the particle exhibits simple harmonic oscillation. You know, and with further analysis of the problem, you'd be able to extract out the frequency of oscillations, which we'll explore down the road. But anyways, I'm going to go ahead and end this video here. If you enjoyed this video, found it helpful, let me know in the comments and consider subscribing to the channel if you haven't already. I love to hear about people getting on board. But other than that, thank you so much for watching.